Please work. Cool. Okay, so there was a question about why can I put the 3 over the 15 and the 10 over the 15? And this goes back to those horizontal versus vertical proportions. Do you remember how we talked about rotating the proportions yesterday? Not yesterday, last class. Okay. So 10, 15, and y are going to maintain the same proportions as 2 this length, 2x and 5. So 2 times some number will give me 10, and x times that same number will give me 15, and 5 times that same number will give me y. Okay? So they're in proportion, but these 3 segments here will be in the same proportion to each other as these 3 segments up here will be. Does that make sense? There's 2 different proportions going on here, and this happens with all similar triangles as well. There's the proportion from one transversal to the other, which happens to be 5. So 1 to 5. So the segments on L are in a proportion to the segments on M, and that proportion is 1 to 5. Now, there's another proportion going on, and we'll call this 1, 2, 3. Okay? This proportion of these 3 segments, segment 1 to segment 2 to segment 3, are the same proportion. It's 2, 3, 5, right? 2 to 3 to 5. 2 to 3 to 5, and 10 to 15 to 25 is the same proportion here. If I simplify, you're not believing me, I can tell by the look in your eye. If I do 10 to 15 to 25, and I factor out their common factor, which is 5, I get 2, 3, and 5 as well. So these 3 segments are in the same proportion as these 3 segments. And from one segment to the other, it's a different proportion. And that's what's happening with the triangles as well. So what I'm really doing is I'm comparing for x, I'm saying that this is equal to the ratio of 1 to 5, right? No. This is the ratio of 2 to 3. So that's the ratio I'm using for this one. I'm comparing segment 1 to segment 2. Segment 1, segment 1. Segment 2, segment 2. Okay? This one down here, I'm comparing between the lines. I'm saying 3 to 15 is the same as 5 to y. Okay? Does that help clarify why you can do that? You can compare between the 2 lines, or you can compare each line to the other line. All right. Now here comes the hard, fun question. And you guys can draw this with me or you don't. But I love the angle bisector theorem. When I first saw it, I was like, I don't believe this at all. I have no belief in what they're telling me is true. I can't even put my mind around it because it doesn't seem like these things would be in proportion. Right, it shouldn't be possible. This cool thing that's happening with them being in proportion shouldn't be happening. So you can choose to draw this with me or you can just watch. That's fine. Okay? I'm going to do my best to make it look like this is the bisector. So I'm explaining why the angle bisector theorem works. And I'm going to try to do it in about 5 minutes. Okay? So here's my angle bisector theorem. And I'm going to ask you to actually prove this later on when we talk about similar triangle proofs. And what the angle bisector theorem says, it says that AB and AD have the same, or excuse me, AB, yeah, I'm going to write that. AB and AD have the same proportion as BC and DC. Or, as I wrote it in the book, we could also say AB to BC, so going across, is in the same proportion as AD to DC, going across. Okay? So, here's how this works. And it works around similar triangles. Okay? We know triangles are similar if all of their angles are the same, and they're the same shape. Right? So what I'm going to do is I'm going to draw a line so that this new line has the same angle measure as this angle up here. So believe me when I say this angle and this angle are equal, because that's how I drew this line to be. Now I know that BD is a bisector, so this angle is also equal. So far so good? Believe me, this is what I've drawn. Okay. What kind of triangle is this triangle if it has two equal angles? It's isosceles. So what do which sides are equal? Which two sides are equal? Yeah, BC and EC. I'm going to call it EC, but yeah. Those two sides are equal. Now, that's cool. I'm also going to prove to you that this triangle right here, the triangle DEC, is in proportion to triangle DBA. So I'm going to try to prove to you that all of the angles in this triangle are the same as all of the angles in this triangle. Here's how I'm going to do it. I already have one angle, and I know these are equal because that's the way I drew them to be. I have another angle that's equal. What other angle between this triangle down here and this triangle up here are equal? The angles at what point? At D, they're vertical angles. How do I know these last pair of angles are equal? Yeah, you could say that. There's a simpler way, though. Well, I think what Jake is trying to get at here is EC is parallel to AB because alternate interior angles are congruent, right? Based on the way I drew this. So I could say that C and A are alternate interior angles, so they're also congruent. Or I could say, how many degrees are in a triangle? Or in all triangles? 180. 180. And if I have one pair of angles that's equal and another pair of angles that's equal, then the last pair must be equal. So far I've proven to you that all the angles in DEC and all the angles in DBA are equal. So I've proven to you that these two triangles are similar. Isn't that crazy? Who buys that? That the two triangles are similar. Not congruent, but similar. One is a dilation of the other. Only 3 people believe me? Who doesn't believe me? You don't believe me? All right. So what about this is too good to be true? Not sure? Well, that's just happened. If I had been more exact with my angle measurements, they would be the same shape. And the way I drew them to be one angle to be equal, right? That's the way I decided to draw this line over here. That was my condition. So I know these two triangles are similar based on the way I drew this angle down here. Pretty cool. So what I can say is that AB compared to AD should be in the same proportion, AB to AD, should be in the same proportion as CE to CD. Because I just proved to you that those two triangles are similar. So I can make a similarity statement. I can make a proportion showing that the sides are proportional. I'm actually really close from going from here to here. What do we notice about these two proportions that I just made? About this one in particular compared to this one? They're the same except for what? They have AB and AD. B and E. One has B, one has E, right? One uses side length CE and one uses side length BC. What do we know about CE and BC? They're equal. So since CE is equal to CB, I can replace this by substitution. What do you guys think? Is that crazy or what? In math, we call this elegant. It means we can't believe it worked out. It's so nice. Okay? This is a true thing, and you guys are going to experiment with it today. Your homework in class is going to be pages 60, 59, and 60.